Exercise 41.14. The exercise is to be solved with the assistance of the TI-Nspire CX CAS version 3.2. Consider the region which is the intersection of the circular regions bounded by the graphs of x squared plus y squared minus 6x minus 4y plus 9 equals 0 and x squared plus y squared minus 4x minus 10y plus 20 equals 0. Part A. Provide a graph of the region. Part B. Provide a graphic approximation of the area of the region. Part C. Provide a calculus calculation which yields a decimal approximation, 5 significant digits, of the area of the region. Part D. Assess the correctness of parts B and C by examining for consistency between the two results. Part E. If able, obtain an exact value for the area of the region. Part A. Provide a graph of the region. I'd like the first page of this to be a summary page and then use all the other pages as support documents. So starting off with going to the menu and adding a notes page and sort of titling the document here. This will be exercise 41.14 solution summary. Here, part A. Also, like that first line, since it's a title, to be more prominent. So let me go back here. We'll select it and go to formatting text. Make that bold. And I think that's as large a font as will fit. Let it go at that. Center it a bit. Okay. Now, the part A, I think I'm going to be referring the reader to page 2 and claim that a graph of the region is on page 2. Alright, so I'll open up page 2, Control, Add Page, Add a Graph. Alright, the graph entry line has already opened up here. Trouble is, it's waiting for a f of x expression, whereas we don't have that. We, at our disposal right now, have these equations for circles. No problem. Go here to the menu. 3 is the graph entry edit. And now let's go under the equation category. And since we have a circle, let's look there. In the circle we have two choices. Perhaps you have the equation in standard form, number 1, or you have it in general form, number 2. We of course have general form number 2. Let's go there. Alright, now we see we have what's going to be called equation 1, which by the way isn't a variable. We can't really use this in other applications of this document. So just make a note of that. And otherwise, let's put in the coefficients we have here. Looking at the original first equation, we have a 1, and of course it automatically puts a 1 for the y, because if it was otherwise you would not have a circle anymore, right? Okay, tabbing across, the x coefficient there is going to need to be a -6. Tab. The y coefficient is a -4. The constant term is a 9. And enter. Okay, got a circle. There's an equation with it. Alright, let's go on and continue then. Let's put tab. It stays within the circle general form context and provides us another opportunity. This works well for us because that's exactly what our second equation is, another general form of a circle. So here we go with the coefficients. 1, tab. The y is already a 1, tab. The x in this case is a -4, tab. The y coefficient, a -10, tab. And 20 for the constant term. And enter. Okay, there's our second circle, and we can already identify the intersection of their interiors there. What we want to do now, though, is make this graph look really nice and have it so that the key region is largely covering our canvas here, so to speak. So I think I will first kind of just pull it over to about here. To keep a good graphic approximation, I would like to have a larger region there. So let's see, I think for that I will start by doing a zoom box. Okay, first corner. Perhaps, I don't need to keep all that whole second circle here. I really want to make sure this is dedicated to the region at hand, so I think I'll put the first corner here so as to retain the y axis, and then come down here, retaining some x-axis. I like to have axes appear in my drawing when I can. About like that. Escape that tool. Now, one sort of disturbing little feature is that those don't look like, certainly the blue does not look like a circle any longer. That's because the axes are not scaled the same. We'll need to arrange that. I think I'll sort of do that right now. Menu, zoom, and zoom square, which is B. Okay, that fixes that up. Alright, this is looking almost fine. I think I need to do a little bit of touch-up here. I like axes having simple numbers and like 3.99, not simple. Okay, and I need to extend that a little bit because I really want to get the full blue circle in here. Alright, so I have some ideas. I'm going to now sort of manually proceed to pick up the rest of this, and that means I'll go to the menu, I'll go to the window zoom, I'll go right to the actual window itself to continue. X-min. Okay, I like to see the y-axis and I want a simple number, so I'll go with a -1 and tap. X-max. Okay, let's see here. I would like to have this x-axis to be, based on what I see, about 6 units long, perhaps longer. And I think I'll make it a 6.5. And the reason for that is now that it is 7.5 units long, the y-axis should be 5 units long. And why is that? Because you always want to make it so that the ratio of x-axis to y-axis is 3 to 2. That's how you keep everything squared up so that there are no distortions in things like circles. Okay, so now I'll continue here to the x scaling. Just one apiece will look nice. Now the y-axis, I want this to be 5 units long, and I want it to contain that a little more than 4. Okay, so I think my plan here will be to go with a -0.5, and then maximize that at 4.5. Scale it one apiece. Okay, so try that. Alright, this is starting to look pretty good. Let's see if I can get things labeled here with, is there room to put a label here is my question. I want to get this blue up here. Okay, I think that will be pretty nice there. I like the scaling at one apiece, looks good, not too dense. The numbers are simple for the axis endpoints, and everything is, the important feature, the region is prominent here, filling a lot of the space, and very clear. Alright, what I'd like to do now is get those points of intersection. Alright, how about that? Let's go here to Menu, and Geometry, Points and Lines, Intersection Points. Alright, with this tool I just need to select the two objects I want intersected, and it'll compute the points. So this red circle, click. That's one object. This blue circle, click there, and there they are, the 2 points of intersection. Now that's a lot of decimal places, and this is just here a graphic approximation sort of thing here, so I don't want such large clumsy looking numbers here. Let's fix that. That can be done by, let me first put away this tool, and I'll go to the menu and go to the settings. Now see, I have the graphs and geometry settings. So this is a settings just for all my graph applications. And I think just a floating of 2 will help simplify the appearance of things here. Okay, I like that much better. Let me move these coordinate labels so that they're not cluttering important parts. Maybe about like so. Now, time to shade the desired region. Alright, the intersection of those two circular interiors. Let's go for that. And to do that, I would like to first sketch a polygon to assist me in this. So Geometry, Shapes, Polygon. Okay. Alright, now let me right click on this polygon and go to color, fill color. I'll choose yellow. Okay, getting there. Now, this shaded polygon is has two purposes for me. One is it helps me get the region shaded, and secondly, it's going to provide a graphic approximation for the area of the region. However, as a graph of the region goes, I don't want to see all these vertices and line segments of a polygon. I just want to see the region shaded. So I'm going to take this in two different directions. I'll make a copy that I'm going to designate for part B usage, and I'll keep one copy for graph of the region purposes. So for that, I'll go to Control, Show Document Pages, and I'll click here and copy it, and click here and paste a copy. Okay, back here. Now this is going to be the graph of the region. So for one thing, I don't want to see black polygonal lines around it. I just want shading, so I go back to the color, and now it's the line color. Change that to yellow. That looks better there. Now all these vertices, with the exception of the intersection points, are a distraction too. So I can get rid of those by taking each point and hiding it, and doing this for each one. Okay, and last thing I might do is, with text, record my designated region here. Okay, about like so, and I suppose that looks like a pretty complete graph of the region. That settles part A. Part B, provide a graphic approximation of the area of the region. Alright, for the approximating the area of the region, I'm going to go to that graph of that has the polygon shaded again. This one is on the next page now. Now I use this polygon to approximate the area. One of the reasons I was pretty careful to put quite a few points on this polygon is I like the approximation to be really pretty good, pretty accurate, so that I will have confidence in comparing for consistency with a future analytic computation. Anyway, polygon here, and this time let's go to a measurement area. Okay, got this 4.7 square units, and then I should add a little text to help the reader know just what is going on in this diagram. Okay, there's my diagram, and let me go back to the summary page, of course, and record what we found here with the 4.7 square units being obtained by using a polygon to approximate the region. Okay. Part C. Provide a calculus calculation which yields a decimal approximation, 5 significant digits, of the area of the region. Alright, let's decide on an analytic calculation strategy here. Since there are some circular arcs, you might think there's a chance to use some plane geometry and simplify the situation. However, there are no actual circles, nor are there any circular sectors, so that kind of deletes the plane geometry simplification. Looks like we're going to need to go all calculus here. So let's try slicing this thing up with thin vertical rectangles and see what that looks like. This looks pretty simple. All of the tops of the rectangles are defined by the blue circle, while all the bottoms of the rectangles are defined by the red circle. Okay, let's go on further and try to formulate the area of one of these thin vertical rectangles. Like any rectangle, the area is going to be length by width. In this case, the length would be, well, I suppose we could just for now say upper y minus lower y, since we don't actually have any formulations running around for that as yet. And the width of each rectangle will be a small piece of the x-axis called dx. So we have in mind summing those areas of the thin vertical rectangles with a definite integral. However, we need to get all the elements of that definite integral in order before we can compute it. All right, let's start with the limits of integration, since we're right here at this graph of the region page of our document. And those little dx's start off at the left point's x coordinate, which is this number here. Let's store that, and we'll call it A1A. I choose an A at first because that's the traditional left-hand limit of integration. I use an A1 because the Nspire recommends you not use single letters as your variables. And now I suffixed it with an A because this is only a decimal approximation of that number, not necessarily exactly it. So that's why I choose this variable name here. And enter. Here's our right-hand limit of integration. The dx's travel as far to the right as here. I'll store this into B1A. Alright, now we had the issue with upper y minus lower y, but we don't have any formulations for those just yet. Okay, that upper y, that comes from that blue circle. So let's try to solve for y for that blue circle. To do that, I'm going to try to bring back the formulation line, and I hit tab, and let's go back up to not the red one, it's the blue one. Now I'm going to push on shift and arrow to the right to select this equation. Alright, and I'm going to go control C to copy that. Now I would like to go to page 3 and then go control add page. Our page 4 will be a calculator application. Now I'm going to go ahead and solve that for y here, so we'll say solve, and now I put my control V, comma, and I want y solved for, enter. Okay, got these two formulations here. What are these? Okay, we have discussed this kind of situation before. Each of these is a semicircle. Okay, and in fact, the left one here, after you distribute that negative sign, you realize this one is a lower semicircle. The one on the right is actually an upper semicircle. When we set up our formulation, what happens for the blue circle is that we actually need its upper semicircle to form the upper y. Okay, so let's go ahead and we'll create that, and we can do it like so. We can grab the upper semicircle, and I'll go by doing this, get this by clicking here, select just the formulation of it, and then I can go enter. That pastes it onto the next line, and now I can go with a control store to. Okay, a function name here. I want something that I can remember, and I think I'll call this upper blue semicircle of x, and so that will be okay. Now the other item was that lower y formulation. Let's go back to our graph of the region here, and this time let's scroll up to the red equation, and we realize that for this we're going to need it solved for y, and we're going to need its lower semicircle. So right now I need to select this equation. I push the shift key and arrow over to the right to get this selected. Control C to copy it. Going to return to my calculator application page 4. And once again, let's solve and control V, paste that equation there, a comma, a y, because that's what we want solved for, enter. Alright, and we notice we have here two formulations. Each is a semicircle, but the left one is a lower semicircle. The right one is an upper semicircle. For the case at hand, we want the red's lower semicircle. So this means I'm going to come in here, click about here, shift, and ever so carefully, make sure you get the negative sign as well, and hit enter. It will paste itself down to the next line for me. And now I can go with a control store to. Now this will be my lower red semicircle of x. Enter. Okay. Now I have my two functions needed to describe the upper y and the lower y. I've also got the limits of integration all stored and ready to go. Looks like we are prepared to compute the integral. So for that, maybe let's go back to the summary page. All right, first a little description to the reader about what we've got going on here. Okay, so to review what we've done here, again, the area of the region can be calculated using a definite integral, which sums thin vertical rectangles. The limits of integration have been stored into variables a1a and b1a. Function formulations needed are obtained on page 4. So we just refer the reader there if they want to read the details of that. Otherwise, let's go ahead to the menu and let's do some calculation. Calculus, integral, and here goes our A1A, tab, B1A, tab. Okay, now it takes a bit of work to type out the names of those function variables, so just use the variables key. And we want, of course, the upper blue circle at x, arrow forward, minus. And now variables lower red semicircle at x, tab dx, and go. Alright, let's see what we've got here. Now this question does ask for 5 significant digits. We're showing too many. Okay, well what we haven't done yet is set up our document for the appropriate number of significant digits here. So let's go ahead and let's go to the document key and go to the settings, document settings. Let's be floating 5 here. Okay, and that number there now sort of self-corrects, 4.7797. Alright, now we could touch this up a little bit. Mathbox attributes. I like that symbol to be, in this case, an approximately equals to, since we haven't got an exact solution just yet. And otherwise, I think here I will just add on the idea of having square units. Okay, there's our calculus calculation with the 5 significant digits. Time to do a assessment of correctness here. Part D. Assess the correctness of parts B and C by examining for consistency between the two results. Alright, let's go back and see what we had expected for a graphic approximation of this. We could go back here to page 3 and review that we have about 4.7 square units. Oh, this is good. Okay, so record that. Now we also have sitting right before us that the calculus calculation is well 4.7797. All right, well, gosh, they only differ by not even a tenth, right? So 0.4 would be a 10%, and then 0.2 would be 5%. So we're easily within 5% of each other on these two quantities, and that would mean these results are consistent, and that would allow us to claim that we really believe that the results are indeed correct. Okay, so there's our conclusion there. This is looking really good so far. Part E. If able, obtain an exact value for the area of the region. The first hurdle to cross in an exact calculation is to be able to have exact limits of integration. We need to get exact x-coordinates for the intersection points of the upper blue semicircle function and the lower red semicircle function. To do that, let's return to our calculator application page, and so that's our page 4 right here. Okay, so here's what we have in mind then. Now I'm going to go to the variables and have low red semi of x equal to variables menu, upper blue semi of x, forward arrow, comma, solving for x, go. Ah, we have succeeded. Okay, that's nice. Now, let's see, what about these numbers here? Well, we know that when the Nspire is solving a single variable quantity and provides a couple specific numbers, they are in ascending order. And so let's go back here and let's say push the shift key, start selecting. Okay, enter to paste this on the next line. And now let's go with control store to. This will be A1. No more approximation, this is exact. Okay, back up there again. This time, shift key, arrow over here to select this number, enter to paste it onto this new line of the page, and again, control store to, this time B1. Okay, we've done that. Now, we have to see if the integral calculation will also give us an exact quantity. Let's go back to the summary page to compute that. First, let's update the reader a little bit about what we've done so far back there on page 4. Okay, we've got the reader updated by saying, firstly, exact limits of integration have been calculated and stored into variables A1 and B1. See page 4. So we are now ready to attempt our evaluation of the integral to get the exact area. Let's go down here and be optimistic here and write. Okay, now I would like to write that integral with the new exact limits of integration. To maybe simplify rewriting it, I think I can go up here and do a little copy and paste of this and then just touch it up a little bit. So I have here shifting and arrow key to grab this. I'll do control C. I'll now go to the end of my document again and control V to put this here. Now I need to go back inside here and put exact limits of integration, which is just a matter of making that a B1. Down here, that's A1. Alright, hit enter. Oh, we've got an exact area calculated. Not simple, but it is. Okay. Pretty nice. Let's see, we need to touch this up a little bit. Yeah, okay, one little adjustment, and that's that we want this to be an exactly equals to sign here. So I'll make that symbol equals to. There, that's it. Okay, we could say, of course, the square units to finish that off. Another remaining issue, though, is this really correct? You know, it's a little unnerving to look at something this complex looking and not be certain that it's right. So let's give it a check as well. Let's write this number as a decimal approximation and see what it comes out to be. So we could write here, for peace of mind. Alright, and now I need to get that number. Let me go back up here. Okay, I've got the shift key on, and let's keep going up. Okay, here's the number, control C. Back to the end of my document, and a space, control V. Now this time I'm going to get the context menu, and as an action, I'll choose approximate. Okay, and that is indeed the same number as we obtained in the decimal approximation of part C. So there's our final check on all of this. This is looking very good. And let me just fix up this box here a little bit. That should say approximately equals 2 for its sign. There. And now maybe a little bit of sentence here. Okay, very good. That does it. Obtained an exact answer as well as a decimal approximation, and we feel confident this is all correct because we've also got a graphic approximation consistent with these results as well. Very good.